Today, science can see into the past, how the sun, the moon, and the earth were formed, how the solar system came together, even the galaxies and the whole universe. We can measure the distance to the nearest star, the nearest galaxy, and look back further still. We can even trace, through science, how space and time have behaved and evolved ever since, and how, much later, living organisms came to be. But there is an edge, a limit of science, of physics, beyond which we can see no further into the past. We call this the Planck length, 1.616255 times 10 to the power of minus 35 meters. The Planck time, 5.391247 times 10 to the power of minus 44 seconds. And the Planck temperature, 1.416784 times 10 to the power of 32 Kelvin, the hottest temperature that has any physical meaning in current physics. Before the Planck scale, we don't know what was there. This unknown region is what we call the singularity. So what we call the Big Bang is not an explosion, even though that's how people often picture it, and it is not some unsolvable mystery either. It is the evidence-based physics of expansion, starting from the Planck scale onward. We don't know how that expansion began, but that it is happening, and has been happening since the earliest moment we can describe, is not a guess. It is observed, confirmed fact. At the Planck time, all four fundamental forces, gravity, the strong force, the weak force, and electromagnetism, are believed to have existed as one single unified force. As the universe expanded and cooled, that unity did not last. Each of these forces is carried by its own field. Then, gravity separates from the other three forces, strong, weak, and electromagnetic, which remain unified a bit longer. This happens right at the Planck time, at the Planck temperature. Next, the strong force separates from the electroweak force, which is still electromagnetism and the weak force combined at this point. This happens at around 10 to the power minus 36 seconds after expansion began. Once the temperature drops to about 10 to the power 28 Kelvin. This is called the GUT scale split, short for Grand Unified Theory. After the GUT split, there was an extremely rapid expansion of space itself, a stretching faster than the known speed of light. Space itself was not traveling, it was expanding. This is called cosmic inflation. Inflation was an extremely brief, extraordinarily fast burst of expansion, lasting only from about 10 to power minus 36 to 10 to the power minus 32 seconds. Expansion continues after this, but at a much slower, more gradual rate. Time passes, and then, at around 10 to the power minus 12 seconds, once the temperature drops to about 10 to the power 15 to 10 to the power 16 Kelvin, the electroweak force splits into electromagnetism and the weak force. Right after the electroweak split, at 10 to power minus 12 seconds, the universe had cooled enough for the Higgs field to settle into a new state 1 with a fixed, non-zero value at every point in space, even without any excitation. The electron field and quark fields had already existed and were already rippling into particles, but massless, moving exactly like the photon does today. But now, interacting with this newly settled Higgs field, those particles, electrons, and quarks gained mass for the first time. This is called the Higgs mechanism. Then, the universe continued expanding and cooling. By the time it reached 10 to the power minus 6 seconds, quarks bound together, held by the strong force, to form protons and neutrons. This binding is carried by the gluon field. Then from 10 to power minus 6 seconds to about 1 second, protons and neutrons existed as free particles, along with electrons which born from the electron field ripple, all moving freely in the hot plasma. When first created, the ratio of protons to neutrons was roughly 1:1, but as the universe cooled, this balance shifted. The W field could ripple, converting a neutron into a proton, or a proton into a neutron, and as it became easier to make protons than neutrons, the ratio settled to roughly 6 protons for every 1 neutron. Between about 1 second and 3 minutes, at around 10 to the power 9 Kelvin, it finally cooled enough for protons and neutrons to fuse together. This period is called Big Bang nucleosynthesis, or BBN. It created the nuclei of the lightest elements, mostly hydrogen, which was already just a single proton, and helium, whose nucleus has 2 protons and 2 neutrons. Essentially, just hydrogen and helium nuclei were created at this moment, with only trace amounts of deuterium, whose nucleus has 1 proton and 1 neutron, and lithium, whose nucleus has 3 protons and 4 neutrons. At this stage, these are still bare nuclei only, no electrons are attached yet. After this timestamp, expansion and cooling continued through a long stretch, from 3 minutes to 380,000 years. This entire stretch remained a plasma, a state of matter in which electrons are not bound to nuclei, freed by the intense heat and energy of the early universe, moving independently alongside free charged nuclei. At the end of this stretch, temperature finally dropped to about 3000 Kelvin, cool enough for electrons to permanently bind to nuclei. The hydrogen, helium, deuterium, and lithium nuclei formed earlier each gained their electrons at this point, becoming the first complete neutral atoms. With this, the universe transitioned from a plasma to a neutral gas. After atoms formed at 380,000 years, the photons, born from ripples in the electromagnetic field, present in the plasma since the electroweak split at 10 to power minus 12 seconds, finally started moving freely since there were no more free electrons left to block them. This light is called the cosmic microwave background, or CMB. It is the oldest light that can ever be observed. Nothing before this moment is visible, because no light could travel freely before it. The universe is now filled with neutral hydrogen and helium gas, spread out fairly evenly. There are no stars yet, no light sources at all, except the fading glow of the CMB. This period is genuinely dark, with no visible light being produced anywhere. Gravity gradually pulls slightly denser regions of gas together, clumping matter bit by bit over enormous timescales. This continues for roughly 100 million to 1 billion years. Gravity slowly pulled clumps of hydrogen and helium gas together, along with tiny trace amounts of lithium and deuterium. As each clump grew denser, the intense pressure at its core stripped the atoms back into plasma and pushed the temperature past 10 million Kelvin. At that point, hydrogen nuclei fused together into helium, releasing energy as photons and heat. Gravity continues pulling hydrogen inward toward the core, but the energy released by fusion pushes outward with equal force, holding that pull in balance so the star does not collapse. This is the birth of the first generation of stars, ending the Dark Ages. When the first generation stars ran out of hydrogen at their core, fusion slowed and outward pressure dropped. With less pressure to resist it, gravity compressed the core further, pushing the temperature past 100 million Kelvin. At that heat, helium nuclei began fusing together into carbon, releasing new energy and restoring the balance between gravity's pull and fusion's push for a while. As helium runs out, the same pattern repeats again. Unlike the earlier stages, this reaction does not produce one single element. Colliding carbon nuclei fuse into a mixture of neon, sodium, and magnesium, all forming at the same time, as different possible outcomes of the same reaction. As carbon runs out, the same pattern repeats. Neon burning ignites at roughly 1.2 billion Kelvin at this temperature. The core itself emits high-energy photons as thermal radiation, and these photons break neon apart, with the pieces recombining into oxygen and magnesium. Oxygen burning follows at around 1.5 billion Kelvin, producing mainly silicon and sulfur. Finally, silicon burning ignites at around 2.7 billion Kelvin, producing iron and nickel. By this point in its life, the star is a layered structure containing all these elements together at once, hydrogen and helium in the outer layers, then carbon, neon, oxygen, and silicon in successive shells beneath, with iron and nickel sitting at the very center. Once the core is made of iron and nickel, no further fusion can release energy. With no outward pressure left to resist it, gravity wins, and the core collapses catastrophically in a fraction of a second. Protons throughout the core get crushed together with electrons, converting into neutrons, forming an incredibly dense neutron core. This conversion is beta decay, driven by the W field. This core suddenly becomes incompressible, and the collapse stops almost instantly, creating a powerful shock wave that rebounds outward. Meanwhile, the outer layers of the star are still falling inward under gravity, and they slam violently into this rebounding shock wave. This collision blasts the star's outer layers out into space at extremely high speed. This explosion is what actually creates elements heavier than iron, like gold, uranium, and silver, and scatters them, along with everything else, out into the galaxy. This is the supernova, the explosive death of a massive star, and the moment that seeds the universe with the heavier elements needed for future stars, planets, and life. That's where we'll leave it for this video. From the edge of physics itself, through the birth of forces, particles, the first atoms, and the first stars, all the way to the elements. A supernova scatters across a galaxy. In upcoming videos, we follow those scattered elements further, how they come together to form planets, how Earth itself formed, and how the first living cells emerged from all of it. If this helped it click, hit subscribe, drop a like, and I'll see you in the next one.